that isn't like total chaos, but I guess we'll find out. All right. Hopefully that was the last bit of chaos all day. Justin's going to try to figure out how to get rid of the chat because it was requested on Ed. So good luck with that, buddy. OK. Cool. Welcome back. OK, hopefully no more chaos all day. So I'll come back to this in a little bit. But today starts with a puzzle. So I'm going to start off today with the mystery of the walrus. Ooh. So what is the mystery of the walrus? Well, the mystery of the walrus goes like this. So take a look at the code on the left. What happens is I create a new walrus, and I give it a weight and a tusk size. And what those numbers specifically mean doesn't really matter. Then I declare there is another walrus variable, b. And then I set b equal to a. And so the question for you is, if I now set the weight of b equal to 5, is that going to change the weight of walrus a? Is it yes? Is it no? You might not have all the tools you need to solve this problem yet, so just kind of try to like feel out what do you think the answer was if you had to take a guess, and then we'll try to go through it together. OK. The second part of the mystery of the walrus, I hope you all are talking amongst yourselves about walruses. OK. The second part of the mystery of the walrus goes like this. So the code on the right has x equal to 5, and then I declare another integer y, and then I set y equal to x. And the question now is, if I set x equal to 2, does the change to x affect y, yes or no? Is everyone talking about walruses, or is there something I'm missing? Shh. I'm going to spoil the answer really soon. OK. OK. I don't know if you're talking about walruses, if you need more time, if you want to see the answer, if you just want to like go home. What are we doing? What are we doing? OK, I'm going to start showing a little bits of the answer, so everyone finish your conversations so we can keep talking about exciting walruses. So here's the code that we had from before. I've shoved it into the Java visualizer. And so now that we're in the Java visualizer, I haven't told you how this thing works exactly, but we can try to see what the visualizer tells us about walruses. Shh. OK, you got to be really quiet. Walruses don't like it when you're loud. OK, so what happens is I set walrus A. There it is. There's my beautiful walrus. And it's got a weight, and it's got a tusk size. And then for some reason that we haven't totally teased out yet, when I say b equals a, the picture is showing me that there are 2 arrows to the same walrus. So now what do you think? Well, if I look at this picture, there are 2 arrows to the same walrus. So hopefully it's not too surprising that if I change the weight of my one and only walrus, this walrus has lost quite a lot of weight. It's now weight 5. It's not surprising that the change to a also affected b, because there's only one walrus. It's the one and the same. OK, so that's what happens if we have the walrus. But this is the second part, and this is what really makes it a mystery, which is when I set x equal to 5, and then I declare y equal to x, well, this time there are 2 5s. So it's not like the walrus where there was just one. So what's going on here? How come when I set x equal to 2, this time the change to x actually doesn't affect y? The 5 is still there. So this is the mystery of the walrus, and that's where we're going to spend the first half of today trying to tease apart. It's really interesting, and something you'll use for probably the rest of your CS career. OK, so what happened was, as we saw, when you change b, it actually does affect a. There's only one walrus. So why is that? And how come it didn't work the same for integers? So to figure out how this works, I'm going to have to dig a little bit into 61C stuff. That's the next class. So bear with me for just a little bit. It's a bit of a preview. So what happens is, on your computer, if you go all the way down to the lowest possible layer of abstraction, you're going to find a bunch of ones and zeros. So somewhere buried deep in your computer, using a bunch of fancy circuits or things that I don't understand, there are a bunch of ones and zeros in one big string. Lots of ones and zeros. And that's how your computer stores data. OK, and what happens is the data that we see has to be encoded as a sequence of ones and zeros to be stored in memory, because that's what memory is. It's a bunch of ones and zeros. So for example, the number 72 is often stored as 01001000. Why is that? 61C will tell you why. For now, you can take my word for it. What about the number 205.75? Well, this is often stored as, and you don't have to memorize this. I won't test you on this. It's encoded as 01000. OK, I'm not going to read it because I'll be out of time. Here are some other examples. The letter H is stored as this string, which happens to be the same ones and zeros as the number 72. And then the Boolean value true is often stored as a bunch of zeros followed by a 1. That's the convention that people chose to use. All the computers agree on it, so that's what we've got. So one thing you'll notice is right away, hang on, the 72 and the H are stored as the same sequence of ones and zeros. So how do I tell if my computer presents me with 01001000, which one is it? Well, the computer is going to figure out which one it is by looking at the type of the variable. So remember in Java, we had types associated with every variable. And in fact, there are 8 types. There are 2 that are bold that you'll definitely have to know about. Some of these we'll cover, some of these we kind of won't. But they are byte short, int long, float, double, boolean, char. So you'll see those as you start programming in Java. These are the 8 primitive types. And we'll talk about what primitive means in just a little bit. OK, so again, 61C if you're interested. So what actually happens when I write a declaration of a variable? We already saw from last week that if you want to use a variable x, you first have to say, I declare that a variable x exists. So what actually happens when I do that? Well, what happens is your computer digs through that giant sequence of ones and zeros, and it finds some sequence of ones and zeros and says, this is the place where my x is going to live. So for example, if I declare int x, what's going to happen is my computer is going to dig through memory. It's going to find just enough ones and zeros to store the integer, and then there it is. So whatever ones and zeros are in this part of memory, that is x. We gave that series of bits a name. And then same thing for y. So if I say I declare that there is a double y, then I'll create a box of bits, and that box of bits corresponds to y. And in the future, if I ever say something like x equals whatever, the Java compiler will see, oh, OK, the x, I know what that is. That's the thing that you named this sequence of bits right here. So that's how the Java compiler knows where to find x or y. OK, so I think that's basically it on this slide. Again, stop me if you have questions. OK, so when you declare a variable, we make this box. And then in this box, we'll hold the ones and zeros that correspond to that variable. And Java will keep some sort of lookup table that says, if you ever reference x, go here. If you're ever talking about y, look over here. OK, so that's what happens when you declare. But then what happens when I assign? So here we can see if I say x equals this big old number, then what's going to happen is I have to figure out this number. What is it in ones and zeros? Apparently it's this. And then I'll shove it in the ones and zeros corresponding to x. And then whatever this is, all that stuff, that goes in y. So that's what happens when you assign a variable. OK, but maybe you and I both agree this is kind of hard to read. When I look at these ones and zeros, my brain starts melting. I don't know what this is. So instead, just to make our lives a little bit easier, we're going to introduce something called simplified box notation. And all that is instead of saying, well, to be really honest, this number in memory is this sequence of ones and zeros, but I can't read that. You can't read that, probably, unless any robots are in the audience. So instead, we're just going to write the human readable representation, and that's good enough for our purposes. OK, great. There's a simplified box notation. More about it very soon. OK, so the next thing we have to figure out is now we know what happens when you declare a variable. You make some space in memory, and you say this is the place where x goes. So what about when I assign a variable? Well, to answer that part of the puzzle, we have to talk about what I call the golden rule of equals. I don't know if this is what other people call it, but that's what we call it. So the golden rule of equals says if you ever have a statement like y equals x, all that the equal sign does is it takes all of the bits in x, the ones and zeros corresponding to whatever section of memory you named x, and we just copy all of that stuff into y. That's it. Nothing else fancy happens. You take all the bits corresponding to x, and you copy them into y. So we don't do any sort of extra creation of new objects. And maybe that's starting to get into what the mystery is all about. But all you have to know for now is that if you say y equals x, you take all the bits from x, and you copy them into y. OK, so hopefully now that I've talked about the golden rule of equals and the way that variables are declared, the second part of this puzzle isn't so surprising. When I say I declare there is an integer x, then what happens is I create a box, and that box of ones and zeros corresponds to the name x. And then I set that equal to 5, because the golden rule of equals says I take the bits on the right, whatever corresponds to 5, and then I copy it into x. And instead of writing ones and zeros, because I can't read that, I'll just write the number 5. And then same thing for y. I declare a different box, and this box corresponds to all the ones and zeros that I named y. So here, when I say y equals x, what do? I copy the bits. I take all the bits in x, which happen to correspond to the number 5. I copy those bits, and I rewrite them into y. And that's why I have 2 copies of the number 5. Then when I say x equals 2, I take all the bits of 2 and I copy them into x, and that's how I get x equals 2, y equals 5. So how come this resolves the way it is? It's because of this golden rules of equals, where I just copy all the bits. OK, good so far. We talked about declaring variables, talked about allocating the ones and zeros, talked about copying all the bits. OK, so that solves the first part of the mystery of the walrus. Now we know how integers behave. But it hasn't solved the second part, which is how do walruses behave? So to figure that out, we have to look at this list of types, and we see there's byte short, int long, float, double, Boolean char. There is no walrus. Java does not have a built-in walrus type. OK, maybe a point of improvement for next time, but there's no walrus type in Java. So if you have any other type that is not one of these 8, including walruses, tiles in your project 0, dogs from last time, I don't know, planets, whatever, anything else that is not one of these 8 types is going to be what we call a reference type. And we'll dig into what that means on this slide, I guess. OK, so anything that's not one of those 8 primitive types that we list, it's called a reference type. And what happens when you instantiate an object is you create a reference to that object. So what does that mean? It's kind of weird and vague and abstract. So let's dig into what happens when I write this line of code. You've seen this line of code before. I'm calling a constructor. And remember, the constructor creates a brand new walrus. So the new walrus is born into the world and then returned to us. So how does that actually work? What does it look like when I create a brand new walrus and have it returned? So what happens when I want to create a new walrus is the Java compiler or interpreter, it needs to dig through memory and say, OK, you want a brand new walrus. Well, walruses are pretty big. In fact, they need to store the weight, and they need to store the tusk size. So they're pretty big creatures. You need to store 2 things about them. So Java is going to go through, dig through all the ones and zeros, and look for a home for my brand new walrus and say, right here, this is the place where my wonderful walrus will live. So let's see that in action. OK, so here it is. I dug through memory, and then I found a place in memory where I can put the walrus's weight. There it is. And I can put the walrus's tusk size. There it is. OK, I don't know if this is a realistic tusk size at all, but I'll have to take the slide's word for it. OK, so here's another picture of it. Again, your memory in your computer is just a gigantic string of like billions and billions of ones and zeros. And what happens is the Java interpreter goes through the memory, and it digs through, and it finds this location, and it says, you know what? This looks like a good place for a walrus. And what it does is it sets some of those bits to correspond to the weight. So whenever you reference this particular walrus's weight, it goes right there. Anytime you ask about the walrus's tusk size, it goes right there. So it digs through memory, and it finds this home for the walrus. And that's all well and good. But now we have a problem, which is, how do I know where to find this walrus? We can see here, memory's kind of big. I put this walrus here. And it's like burying a treasure in the field. If I go to the field and I bury a treasure, and I don't write down where I put it, what's going to happen? I'm going to lose the treasure forever. And walruses, they are very treasured objects, and I don't want to lose them. So what can I do? So what's going to happen next is, when I created the walrus using the constructor, Java went into memory, and it created this beautiful walrus. Look at it. It's gorgeous. And then problem is, we need to figure out, where's the walrus? Where was the walrus? I want to visit it later. So how do I find it? So what Java is going to do next is, one way you can think of it is this new keyword is going to shout to the heavens and tell everybody the location of this brand new walrus. So just like when I bury treasure in the field, I got to know where to find it. When I create my brand new walrus, I need to write down somewhere where I put this walrus so I can go back and visit it and change its weight and feed it food later. So how am I going to do that? Well, what Java is going to do, what this new keyword is doing is, it's going to take all of these bits, and you can kind of think of it as, I could put a number on each of these bits. I could be like, that's the first one, and that's the second one, and that's the third one, and that's the fourth one. And maybe, just maybe, this walrus lives at the I don't know what this is, 238472342 bit of memory. OK. So what the new keyword will do is it will shout to the heavens and tell everybody, this walrus that you just made, it lives at bit number, whatever that number is. That's what the new keyword returns. So you can almost think of the new keyword as returning a number. What number does it return? It returns this number. Why? Because that is the numbered bit where my wonderful walrus lives. So this new walrus constructor does 2 things. First, it allocates the memory and says, this is the home for the walrus. But if I don't write it down, I'm going to lose it. So the new keyword helpfully says, that's where it lives. This number, if you go to that numbered bit in memory, you will find your walrus. Excellent. Okay. So that's great. That tells me what happens when I create a new walrus. But like we said, if I don't write down this number, I will lose my walrus forever. And I don't want to lose my walrus forever. So what happens next is I need somewhere to put that location that I just wrote down. So where do I put it? That's where this line comes in. So when I say walrus sum walrus, I am declaring that there is a variable of type walrus. But remember, there are only 8 primitive types. Walrus, not a built-in type in Java. So when you declare walrus sum walrus, what you're actually getting here, and if all of this is gibberish to you, this is the one thing you need to fully understand the mystery. When I declare there is walrus sum walrus, this space right here, these 64 bits, the ones and zeros, that's not actually the walrus. I know it looks like a walrus, right? This looks kind of like a walrus, but it is not actually the walrus. Instead, this location is going to store the location of where the walrus actually is. I'll say it one more time because it's so important. When I declare there is some walrus, this memory box does not actually contain the walrus. It doesn't fit. Remember, the walrus is really big. It had the tusk size and the weight in pounds. This is not going to fit the walrus. This space is just telling me where to find the walrus. It's like a little note to myself that says, if you want to go visit your walrus, you got to go here. OK. Here I have assigned it to null, which is a bunch of zeros, which indicates there is no walrus. Kind of depressing. So let's make a walrus. So when I say new walrus, blah, 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 what happens is, well, 1008.3, what happens is the walrus constructor, it digs through memory, it finds the glorious place for the walrus, and then the new keyword shouts to the world, your walrus is located right here at this bit of memory. And then here there's an equal sign. Equal sign. What do we know about equal sign? Well, the golden rule of equals says I copy the bits from the right and I assign them to the left. What are the bits on the right? Well, we know the new keyword is shouting to the world. It's telling everyone, your new walrus, it lives right here in memory. This is the location. So I take those bits, which tell me where the walrus lives, and then I copy those bits into some walrus. And now some walrus, this variable, doesn't actually hold the walrus. It doesn't fit. The walrus is too fat. Instead, this space, it holds the location of where my walrus actually lives in memory. So this sequence of ones and zeros, I know it looks like a walrus. It is not the actual walrus. This tells me if I go to this location in memory, I will find the walrus that I seek. There it is. It's got its weight and its tusk size, and it's sitting there doing walrus things. I don't actually know what walruses do in their free time. OK, maybe they read. I don't know. OK, great. So that's what the golden rule of equals does. When I assign a new walrus, I put it in this some walrus variable. And again, I cannot say this enough. It does not store the actual walrus. It stores a reference or the location of where my actual walrus is if I ever want to go visit it. OK, questions, thoughts? This is probably the most important slide. So if you must go to sleep, make sure you get this one. OK, great. So again, this is kind of hard to read. I do not want to draw diagrams where I have to write tons and tons of zeros and ones. So just to make my life a little easier, I'm going to use something called box and pointer notation. So instead of writing something like this, where it's like, this is the sequence of ones and zeros where the walrus lives, and then at this sequence of ones and zeros, that location, I store the weight and the tusk size, that's too hard to read. So instead, I'm going to draw an arrow. And what this arrow says is, in this memory box right here, it doesn't look like it, but there's an actual number there. What does that number correspond to? It corresponds to a location in memory. And if I go to that location, it's like going into the field and digging up my treasure. I go to that location, and I find the walrus. I guess walruses don't live in the dirt, do they? But I'll go to that location, and I'll find the walrus that I seek. So that's what the arrow corresponds to. It says this some walrus memory box doesn't actually contain the walrus. It just contains the location of the walrus. So that's called box and pointer notation. And that's what you saw earlier. OK, great. So at this point, hopefully it is no longer surprising that given what we know about reference types, given what we know about the golden rule of equals, hopefully now we can put all the pieces together and we can finally answer the mystery of the walrus. And the mystery says, well, I create a new walrus, or I declare a new walrus variable a. And again, this is so key. I cannot say it enough. If I look at this a memory box, it does not hold the walrus. The walrus is not going to fit in there. It's too small. So this memory box can only hold a reference to where the walrus is. Sometimes people call it the address of the walrus. It's like the walrus lives somewhere. I will write down the address where it lives. Sometimes people will call it the location of the walrus. You could hear people say it's a pointer to the walrus. So it kind of points you in the right direction. So lots of different things you could call it. But the important thing is that this a memory box, it's a reference to the walrus. It's not the real thing. So when I say I declare there is a walrus variable called a, I have not actually created a new walrus. No walruses exist in the world right now. I just created a place where I could potentially write down the location of a walrus if I ever had one. One tiny little note I'll make, because I think I forgot to do it earlier, is that if you have not assigned a to anything, here the box doesn't have anything, it's still going to have stuff. It's going to have some ones and zeros, maybe left over from last time, but Java is not going to let you access them because you haven't set them to anything yet. So just putting that out there in case anyone's curious. OK, now we come to the next line. This next line has a bunch of things that it's doing, so let's go through them one by one. First, I call the constructor. What does the constructor do? It digs through memory, and it looks through all the ones and zeros, and it says this. Yes, this is the place for my beautiful new walrus. And it says these bits correspond to the walrus's tusk size. These correspond to its weight. And there it is. OK, but I don't want to lose it. So what the new keyword is going to do is the new keyword will shout to the heavens and say, well, the walrus, it lives right here. It lives at the 2,380,000 whatever bit. That's the numberth bit where the walrus lives. That's what the new keyword shouts. Then what does the golden rule of equals do? It takes whatever the new keyword is shouting, which is the location of my brand new walrus, and it copies it into the variable a, which is this sequence of bits right here. So when I run this, a bunch of different things happened. The new walrus got created. Now it lives in memory somewhere. The new keyword shouted to the world where it lives. And then the golden rule of equals copied the location of the walrus into a. OK, beautiful. What happens next? Now I'm going to declare another walrus b. And again, when I declare the walrus b variable, I am not creating a new walrus. Only the new keyword can do that, and the constructor. So when I declare there is a walrus b, all that I'm doing is I'm creating this memory box. And what does it hold? It doesn't hold the walrus. Walrus won't fit. It will only hold a reference to wherever the real walrus is. And like we said before, right now, whatever ones and zeros are in here, you can't access it. Java's not going to let you. So who knows what's in there? OK, and now comes the punchline, which is b equals a. What do? We copy the bits. There's no fancy walrus shenanigans going on. When I say b equals a, all I have to do is I look in a. What are the ones and zeros in a? Well, the ones and zeros in a, they tell me where to find my wonderful walrus if I ever want to visit it. So I take those bits, I copy them into b, and now b holds the same sequence of ones and zeros, which is the location of the same walrus. So it's like two pieces of paper, and they both have the same location of the walrus. So if I use a to visit the walrus, or if I use b to visit the walrus, I will go to the same walrus, the one and only walrus that we've talked about all lecture. There it is. It's sitting right there with its big old weight. OK. Great. So now we've kind of solved the mystery of the walrus. We now understand why when we use primitive types, so if it's byte, short, long, int, double, whatever, those 8 types, then those types, you can put them directly in the memory box. So remember from before, let's go find it. X and Y are ints. I can put the integer directly in the memory box because they are primitive types. Anything that is not one of those 8 types, like a walrus or a tile or a dog, those are reference types. So instead of putting the actual walrus in the box, because it won't fit, we're going to put the location of where the walrus actually is. And then from that, the golden rule of equals tells us that when I set a or b equal to a or y equal to x, I copy all the bits over. And with that, we have solved mystery of the walrus. Anyone have questions about the mystery, why it resolved this way, primitive types, reference types, anything exciting going on Zoom?
Oh, yeah, tons.
Tons of exciting things going on Zoom. OK. I will not inquire further. OK, anything else? OK, cool. That's the first half of today. I guess one final thing I'll note before we move on for good is the golden rule of equals also works when you have arguments. So here's a little piece of code. It's not super interesting. It takes the average of 2 numbers. And the most interesting thing that happens here is, well, what happens when I call average of x and y? How do the numbers 5.5 and 10.5 get sent over to the average function? Well, again, you don't actually see the equals explicitly here. But the golden rule of equals, it still holds. And it says, when I pass the argument x into average, what I will do is I will declare there is a new double called a. And then I will copy all the bits from x into the memory box for a. Same thing for b. I declare there is a double called b. And because I'm calling average with this series of bits, the 10.5, I copy that into b. So whether they are doubles or walruses or planets or dogs, whenever I have an argument to a function, I will copy the bits into that argument. So when I pass in arguments, it follows the same rules as the mystery of the walrus. I copy the bits over. There isn't explicitly an equal sign between the x and the a, but you're still copying the bits over. So just wanted to note that really quickly. OK, so here we see it. There's the x that faded in. There's the y. Perhaps there will be an a and a b. There they are. And so the bits get copied from x to a, and they get copied from y to b. And in this case, a double is one of those primitive types. It's one of those 8 that we saw from earlier. So the bits actually get copied. If x, y, a, and b were walruses, if I was trying to average walruses, whatever that means, then instead of copying the 5.5 over, I would copy the location of my one walrus. And there would be 2 arrows, x and a, that both point at the same walrus. OK, cool. That's parameter passing. That's arguments. Sometimes you'll see this called pass by value. It's like a little vocabulary term. So if you ever want to show people how smart you are, you might call it pass by value. But just noting it here, not an important detail. OK, to summarize the first half of today, we talked about the golden rule of equals. And we said that in Java, there are 9 types of variables. I don't need you to memorize them, but the 8 primitive types are byte short, int long, float double, boolean, char. There they are. If your variable is of one of those 8 types, they can fit directly in a memory box. If it's not one of those 8 types, like a walrus, then it is a reference type. And a reference type says you can't actually fit the object in the box. You're going to write down a reference, an arrow, to where my object really lives. And if there is no object, what if I declare there is a walrus b, and I set it equal to null? I could also fill this box with zeros, and that would indicate the absence of a walrus. It would mean there is no walrus there. So if you ever have a reference type, you can also set it to null, indicating there is no object. I am not referencing anything right now. OK, here's box and pointer notation. You'll see it over and over again. The way that we draw it is every variable gets its own box. And if you ever have references, you'll use arrows. So don't actually write out the ones and zeros, because I can't read that. You can't read that. So instead, we'll draw arrows just to make things look nicer. And again, what is the golden rule of equals? When you say b equals a, you copy the bits. Copying the bits could be the number 5 getting copied. It could be the arrow being copied. But you always copy the bits. That's it. Golden rule of equals. Mystery of the walrus. There's a quiz, but since we started late, you can do it at home if you want. There's a link to the answer if you're curious. OK. Good so far? Question? You got me. That's a great question. The question was, what about capital I integer? You might have seen that in homework 0. I'm not going to talk about it too much now. Ask me later. There's a video on it that's like 10 minutes. But if you use capital I integer, that is an object version of the integer primitive type. So short answer. OK. But it behaves more or less the same as an integer type for all intents and purposes, at least in homework 0. OK. Hold on. I have more, so don't go yet. So I'm going to talk a little bit about arrays. And then we'll go on to the second half of today, and we'll build a list. OK, so really quickly, we'll talk about arrays in way more detail in a couple of lectures. But just really quickly, since you've probably seen them already, when you want to declare an array is not one of the primitive types. I go back and I look at the primitive types. Look, no array. So if I want to make a new array, I have to use the new keyword. I have to instantiate the array, just like I would any other object. And arrays also behave like reference types. So all that this slide says is if you create a new array, like I declare there's an int array called a, the array is not going to fit an a. This is only going to fit a reference, the address of wherever my array really lives in memory. OK, that's all that this slide says. So I declare that there's an a. When I use the new keyword, it actually creates the array and shouts the location. And then if I assign it, then I get this arrow pointing to wherever my wonderful array is. OK, question? The question was, what if you try to create an array without using this new in syntax? I'm guessing you'd get a syntax error, but there are some weird ways to create arrays, so I can't promise. But for now, if you want to create an array, do that. Question? The brackets, this is just some Java syntax for creating an array and filling it with these items. So a bit more syntax trivia, not something I'll talk about in too much detail, not something you have to memorize. Last question. Yeah, that's a really good question. And And this question will really like deeply test your understanding of the mystery, which is, what if I had an array of strings? Well, then what would happen is each of these boxes, they're not going to hold the strings because strings are not primitive types. They will hold addresses to each of the strings because string is not one of the primitive types. Yeah, that's a great question. OK, I know you have more great questions, but I'm going to keep going to the second part. OK, everyone, conversations are done? Shh. OK, you have to be really quiet because I want to talk about int lists, and they're super exciting. OK, so that was the first part of today, golden rule of equals. So I guess to quickly rewind to the first slide that I skipped over earlier, the goal for the second half of today, and in fact, for the next like 4 or 5 lectures, is we're going to build a list. Why the heck would we want to build a list? Well, the main reason is because in Java, arrays have a fixed size. When I declare that there's a new array of size 5, it's going to be size 5 forever. And I can never add more than 5 things into my array. So what if I want a list like in Python where I can add more than 5 things and my list can grow as I have more data to add into it? To do that, I'm going to have to build a list. Lists are not built into Java, so we're going to have to build it ourselves. So let's go on a 3-lecture journey, and let's build some lists together. OK, so we'll talk about our first type of list today, and then we will keep going, and we'll build more lists if you come back next time. All right, I'm going to jump into IntelliJ. Hopefully, everything is nice and readable. Yes? No? Should I make it like bright pink or something? OK, I think it's readable. So I'm creating a new class called intList. It's not going to be immediately obvious what I'm doing first. Maybe if you've taken 61A, you have a vague flavor for where this is going. But I'm going to say my intList object has 2 instance variables. So every intList that I create has 2 attributes or instance variables. Here they are. I'm going to have an integer called first. And then I'm going to have, and this is mystery of the walrus stuff, I'm going to have a reference to another intList, which I'm going to call rest. So this variable, can it actually hold the intList itself? No. It can hold a reference, the address, where can I find my other intList, so I can go visit it and feed it. Wait, I guess you can't feed intLists, I think. OK. In any case, there's my intList. And it seems kind of bizarre, but believe it or not, we're done. That's our intList. And that doesn't mean you can go home, so stay in your seats. But the reason why this is all we need for our intList is, well, let's start building a list together. So here we go. I'm going to write public static void main, a little trick for you. And we're going to start building a list. So I'll say I declare there's an intList variable called L. It can't hold the actual list, but it can hold a reference to a list. So I'll declare, or I will instantiate a brand new intList. I'll assign it to L. OK, well, that's not a super interesting list. I'm going to put stuff inside. So I'm going to say L. Well, you've got a rest, and you've got a first. So I'm going to set your first equal to the number 5. Why? I don't know. I like 5. OK, and what about your rest? Well, I have nothing else to add to this list at the moment, so I'll just set it equal to null. Great. I made a list. It's got the number 5 inside, nothing else. OK, I see you are not satisfied, so I will add more things to the list. So this time, I'm going to say L.rest. You know what? I don't like that being null. I want to have more stuff in my list. So I'm going to set L.rest equal to another intList object. So I've created my second intList object. And I'm going to say L.rest. Oops. L.rest. Well, you are an intList object, and you have a first, and you have a rest. So I'm going to say your first is 10, and your rest is null. Now I have a list with 2 items, 5 and 10. But I want more. So I'm going to say L.rest.rest. You are a brand new intList. Great. And then L.rest.rest. OK, your first item is 15. Oops. And then your rest is null. OK. And I look at this, and I'm starting to get a headache. I don't know about you. So I don't know what is going on anymore. So I'm going to jump into my helpful Java visualizer to tell me all about what's happening. This is the code from earlier, just a lot brighter. And I'm going to look at this in pictures to see what's going on. So here I go. I'm going to create my new intList. There it is. Beautiful. L points at the intList. It's got a default value for first and a default value for null. OK. Then I set L.first equal to 5, L.rest equal to null. It's great. There's my 1-item list. But I want more, so I'm going to say L.rest. Actually, you know what? I don't think it should be null. I think it should be a reference to another intList. This tells me where to find the next item in the list. And that next item is going to have a first of 10 and a rest of null. Looks good. But I want more. So I'm going to say L.rest.rest. So that's L, follow the arrow, .rest. That's this attribute right here. Takes me to this intList, .rest. You know what? I want this memory box, which is currently null. I want this to point to a brand new int list. There it is. And I'm going to fill in the first there with 15. OK, it looks great. There's my 3-item int list. It's got 5, 10, 15. OK, so where's my slide? OK, so I don't know. Maybe you like that. Maybe you didn't like that. To me, it's a little bit ugly. Maybe you like programming like this. To me, I'm like, if I want to make a list with like 50 items, have fun with that. So I'm going to clean this up just a little bit. And I'm going to try building the list backwards to see if it's any cleaner. So let's go backwards. I'm going to say public int list. I'm going to make a new constructor. This is a blueprint for how to create new int list objects. And I'll say it takes in 2 arguments. And I'll use those 2 arguments to set the first and the rest. So I'll say first equals f, rest equals r. This way, if I want to create a new int list, I can use this constructor that has been provided. So let's try to use this. And I'll build the list backwards this time for reasons that will become clear very soon. Don't worry. So I'll make a new int list, takes in 2 arguments. So I'll give it a number, 15 this time, because I'm building backwards. And I'll say the rest, it's null. I have nothing else for now. That's a 1-item list. It's got 15. I look at this and I say, you know what? I changed my mind. I actually want L to be an int list with 2 items. So I'm going to set L equal to a new int list. And this time, the first item is going to be 10. What about the rest? What is everything else? Well, everything else is my list of 15, which is right there. So I'll say everything else, that's L. OK, great. But I want more. So I'm going to say, actually, I changed my mind again. I want L to be a reference to a new int list with the front item being 5. And the rest, what is everything else in this list? Well, it's whatever L used to point to, which is the letter L. Great. So that works just fine, too. Again, might look a little bit confusing. So I will hop into our ever-faithful Java visualizer to see what's going on. There it is. So again, I declare, and I create this new int list. There it is, 15 null. Then I say, you know what? I changed my mind. I want L to point to a new int list with the front being 10, the first item, and the rest being L. What is L? L is a reference to this thing that already exists. So if I step through, OK, first, rest, and eventually I get, so this is the crucial step right here, right? L gets reassigned to a new int list right here. That's the one I just created. First is 10. And what is rest? Rest is the 15. That's what L used to point to. OK, I'll do it one more time just for giggles. So what happens again? This time, I create first, rest. There's my brand new int list. And then here's the key step. I say, well, L used to point to the 10. I don't like that anymore. I'm going to point you to the new int list, which has a first of 5. And the rest is whatever L used to point to. So that's me building the list backwards. And I still got the same list type. OK, looks great. Questions, thoughts? OK, so this list, it works perfectly fine. If you wanted to, you could go out and use this list in the world. But I'm going to say this list is a little bit featureless. Because imagine if I took this code right here, and I gave this to the outside world. And I said, all right, that's what you got to use for your list. This is the Java built-in list. Well, what if a user wants to figure out the size of the list? What if the user wants the 10th item in their list? What if the user wants to add items, delete items? They're going to have to figure it all out themselves, because this class that I have published to the world, it does not have any of those features. So then it'd be up to the user to make their own calculations for the size of the list, adding things to the list. I don't like that. I want to make life easy for my users. So I'm going to add a couple more methods just to help my users be able to use this list. So let's go ahead and do that. Certainly, I don't want my users to have to calculate the size of the list themselves. So let's give the users a size method. It's going to return an integer. OK, great. So, and I'll write a comment just to remind myself what's going on here. So I'll say returns the size of the list using recursion. Why recursion? Because I want to practice it together. So let's do some recursion. So remember, how does recursion work? Well, first I got to think of my base case. The base case is, what is like the simplest possible list I can think of that I could call size on? Well, I don't know about you, but I feel like a very simple list would be a list where the rest is null. If the rest is null, this is a very small list. How big is a list if the rest is null? Audience participation. How big is the list? 1. OK, amazing. So I'll return 1 if the rest is null. Otherwise, my list has more than one thing. So how do I know how big the list is? Well, I want to use recursion. So I want to be able to call size again on the rest of my list. So how do I do that? Well, I could say, well, how big is the rest of my list? I don't know, but look right there. I could just call size on the rest of my list. So I'll say, the rest of my list, I don't know how big you are, but I'm just going to call size on you, and you're going to tell me how big you are. And am I done? Not quite. There's one thing, because however big the rest of my list is, how big is the total list? It's one bigger, because I have to count my item plus the size of everybody else. So I will return 1 plus the size of however big everybody else the rest of my list is. So that's my recursive size method. As we said last time, if you feel more comfortable saying something like this.rest.size, you can do so. But this here is kind of optional, but more of a Java syntax thing. OK, so this size method, it looks great. I'm going to go into the visualizer so we can witness it together. So I'm going to create my list. OK, that's a lot of scrolling. I'm going to create my list. Eventually, it will be created. OK, now it's time to call size. So here I'm calling size. Well, what happens? I start at the very front, and I say, is my rest null? I look. There's an arrow. It is definitely not null. So I'll skip this case, and I will return 1 plus however big my buddy is. So I'll go over to my buddy, and I'll say, how big are you? And the buddy will say, I don't know. Let's call size to find out. And the buddy thinks, is my rest null? No. OK, so I got to ask my buddy to the right, the 15, how big are you? So I go over here. You see how I'm calling size over and over again. Now I'm calling size on, the arrow tells me, on this int node right here, int list. It's got first to 15. And it looks at its rest and says, yeah, my rest is null. I'm a tiny list. I have no further items. So my size is 1. So it returns 1. It shouts to the world. It tells its buddy, hey, I'm of size 1. And the buddy says, OK, well, you're 1. I have one more item. 1 plus 1 is, oh, it's 2. OK, wonderful 61B knowledge. 1 plus 1 is 2. And so this item returns 2. Then I go back here to my original first int list, and it says, well, my buddy said they were 2, and I have 1 extra item, so that gives me a total of 3. That's my recursive size method. OK, questions, thoughts? I have 2 more functions to show you, so don't go home yet. OK, so this size method, it works perfectly fine. Now users don't have to write their own size method. They can just use the one that I've provided to them, which is quite nice. But just to see what happened if I didn't want to use recursion, I'm going to write a different method. It's still going to return the size, but I'm going to have it returns the size of the list using no recursion. So this time, I want to do it iteratively just to see what the pattern looks like. So how would this work? Well, common thing I'm going to do is I'm going to write or declare a new int list pointer. Is this creating a brand new int list with a number inside? No. All that this will fit is an arrow that points at one of the int lists. And what I'm going to try to do is use this little pointer. It's like my little finger. I'm going to count like 1, 2, 3. So I'll use this little pointer to scan through the list. So I'm going to start it at the current item. What's the current item? How do I find the current item? The current item is this current item. Then I'll say, OK, well, while p is not equal to null, so if I scan all the way through, I'm going to keep scanning till I fall off the end or my finger goes to the end of the list. And I'll say p equals p dot rest. So that's taking this p and incrementing it all the way through the list. And as I go, I want to keep track of my size. So I'll say size, you start at 0. Every time I find a new int list, I'm going to take total size. I'm going to add 1 to it. And then when I'm done, I'll return total size. OK, looks great. For time reasons, I'm not going to demo it in full detail. There is a visualizer link if you're curious. But you can play with it a little bit. And what you'll see is, if you look at the p, it's starting at 5. And then we skip over. Now it's pointing at the 10. Then I skip over. Now it's pointing at the 15. So that's iterative size. OK, maybe stuff you've seen before, but we'll code it anyway just for completeness. OK, final thing before we all go home. This one's a little bit challenging, so we'll try and do it together. And if I don't get through it, you can think about it at home. One thing I want to give to my users is I want to let them be able to get items from my list. I don't want the user to write something like l.rest.rest.rest.rest.rest.first. It's kind of annoying. I want to be able to give the user a way to access the 5th element of their list. So I'm going to write a method called get. OK, so let's write the method called get. Wait a minute, I can't go home yet. I haven't written get yet. So I'm going to write get. And I'm going to write a little comment just to remind myself this returns the ith item in the list. Okay, I'm going to write it recursively. If you want to write it iteratively, you can, but I want to practice some recursion together. So let's write get recursively. What is the base case of get? What is the easiest possible thing to get given a list? Well, I look at my list. The easiest possible thing to get would probably be the first thing, because it's right there. So if the thing being requested is the 0th item, 0 indexing, then what do I return? I just return my own first item. I could also say this.first if you wanted to, same thing. Otherwise, and this is the part that's a little bit tricky, so blink and you'll miss it. So now what do? How do I recursively call get if the item that they want is not the 0th item? So one way to think about this is if I look at my list and I like drawing pictures or something like this, I look and I say, what if I want item number 10? So I'm like, I'm here. I want the thing 10 people behind me or 10 items behind me. Well, whatever is 10 behind me, if I ask my buddy, is it 10 behind my buddy? No. How far away is it from my buddy? It's 9 behind them. So I'll say that one more time. Whatever is 10 behind me is 9 items behind my buddy. And then my buddy is going to be 8 items behind their buddy. And then when this 15 asks the person next to it, it's going to be 7 behind them, and so forth. So the punchline is, if I want to recursively call get, I'm going to call get on the rest of the list. But I can't say, hey, whatever's 10 behind me, my buddy, what's 10 behind you? I should ask my buddy what's 9 behind them. So instead of getting their ith item, I'm going to get their I minus 1th item. So let's give that a shot, see if it works. If it doesn't work, you can play with the visualizer and get familiar with it. But I can get, say, the second item in the list. Hopefully I'll get 15. Maybe not. You're also antsy. And if I call L.get1, then I can get 10. OK, it's 2 o'clock, and you are all super antsy. So you can all go. If you want more practice, there's more. OK, bye. OK.